Hi, welcome to your first vodcast, which is meant to be a supplement to your reading on systems, or rather on planetary boundaries. And before I go on, let me first say that if you are feeling fuzzy about basic systems terminology like emergent properties, feedback, lag time, please do watch the vodcast I linked in the syllabus. It's a vodcast I made for biology, so if you're in my biology class, you've already watched it, but it might be still good review. Regardless, look at the syllabus, the matrix of learning goals and key terms, and make sure that you can do all those, and if not, watch that vodcast. So now let's start this. Really, this vodcast is meant to be a supplement to your reading, Safe Operating Space for Humanity. But I wanted to give you some terminology to help with that, and then will help our discussions about lead and actually every topic throughout the entire year. Now, we're going to start here talking about boundaries. So if you look at this concept map, or concept blocks really, that I put together here, I put boundaries way down at the bottom. But your first reading is about 9 planetary boundaries, and what I think will be helpful for you is to get a visual on what a boundary actually is. So what I want to do is have us look first at climate by looking at temperature. I'm going to show you a graph here now. This is temperature change, essentially. So we're looking at disturbance to temperature as a proxy for environmental suitability, and that'll make more sense as we go along here. And here you can see the Earth passing over basically temperature change for the last 100,000 years. And for most of that period, there was great variability. A few degree change is a significant change for climate. And so these are crises that we believe led us to leave Africa, led us to colonize Australia, led us to leave Asia for Europe. Major events. And it wasn't until about 10,000 years ago that we entered the Holocene. And this is what is a relatively incredibly stable time period as for temperature, and that stability we believe has allowed us through agriculture primarily to create the amazing civilization that we have. And without that stability, there is some significant question about whether human civilization would exist at all. Okay, so your reading is on the 9 planetary boundaries. Now, I want to use the climate example to help you understand some of these terms. So we're starting down here in boundaries, and we're going to work our way back up, and that'll be the reason for that, I think, will become clear. So let's jump back to this climate model. Here is the Holocene. This is the period we've been in for the last 10,000 years. Within that period, temperature, average global temperature, fluctuated by basically around 0.5 degree. And within that time period, we had some major weather events, at least we believe we did, at least in the northern hemisphere, things like what we call the Little Ice Age, or the medieval warming period. And those occurred within just 0.5 degree, as opposed to the 3 degrees of change that we're expecting that could cause things like weather pattern shifts, like extended droughts in the western United States, kind of like the one we're having now, but perhaps more long term, or places where there's greater rain, increased precipitation, or massive ice sheets like the Antarctic ice sheet, or in Greenland, melting, which are some of the concerns we have with potential future changes on the path we're on now. So you'll see the paper proposes a planetary boundary for climate, and that's actually 350 parts per million of carbon dioxide in the atmosphere. They're saying that that's the threshold. If we go over 350 parts per million carbon dioxide in the atmosphere, then we're going to change the climate system. So let me explain that a little bit. Look at these 2 troughs with the peak in between. Imagine that this is the state of our climate. And a state is really the way a system is functioning given all its attributes and couplings. And so a coupling is the relationship between 2 parts of a system. So in this case, in the climate system, we have how the atmosphere functions given the amount of greenhouse gases in it. We have the ocean based and how it absorbs greenhouse gases from the atmosphere. We have things like ecosystems that can produce things like carbon dioxide, and they also can absorb things like carbon dioxide. And of course, we have things like ice sheets that reflect energy back into space, or if they melt, more energy is absorbed. So each of those would be parts of our climate system. And each of them are leading to that half-degree change I described during the Holocene. So if this is cooler, then as this little ball, which represents our climate, rolls this way, the climate on the planet is getting cooler for that shorter period of time. So this, if it rolled up here, that might be the Little Ice Age. And as things get cooler, there's some mechanism in the climate system that causes things to get warmer. Maybe as things get cooler, more greenhouse gases are released into the atmosphere, and the planet warms. And as it gets warmer, more greenhouse gases, let's say, are removed from the atmosphere, and the atmosphere gets cooler. So the concept is our climate would rock back and forth through here. And no matter what the minor disturbance, perturbation is a minor disturbance, something that when it occurs isn't going to change the function of the system. So if you have one of those minor disturbances, our climate system will still recover. And for example, volcanic eruptions is a great example. We have a nice geologic record of various eruptions, and what volcanic eruptions do, they put things like sulfur dioxide in the atmosphere, and sulfur dioxide acts as an aerosol in the atmosphere, and it can reflect sunlight back away from Earth, increasing the albedo of the atmosphere, mostly also in clouds, and thus cooling the Earth. And so what we see is after an eruption, we see a period of cooler temperature. So this is change in temperature. This is from what we call the average temperature for a given time period. So here you can see before the eruption you have small oscillations. You can see they're only about a tenth of a degree. And then after the eruption you have more significant cooling for a period, but then the climate system adjusts. So what happened is the eruption caused cooling, and then sulfur dioxide is removed from the atmosphere through atmospheric processes that we'll talk about, like deposition. And so the climate is rocking back through. Now, if you have a major disturbance, which we would call a forcing event, you can actually force the climate system up and over this hill into a new trough. So here you had a stable equilibrium state. Once the forcing event occurred and the climate rolled up here, it reached an unstable equilibrium state, meaning it wasn't going to return back into that oscillation. It's now reached a new point. And that new point, for instance, might be a climate that has an average of 3 or 4 degrees warmer than it is now. And what that would look like on planet Earth, we believe, is significantly higher oceans, reduced ice coverage, reduced glacial coverage, significant changes to weather patterns. Some places get more rain and snow, but many places are drier. West coast of the United States expected to be much drier. The drought we're experiencing now would be par for the course. And so we're very concerned with these forcing events. And so the planetary boundary that your article describes of 350 parts per million of carbon dioxide, crossing over that, they're suggesting might be a forcing event that might force our climate from its current stable equilibrium state to an unstable state in which it reaches a new stable equilibrium, but at a higher temperature, and it would be much harder for us to get back into our current range of temperatures. I hope you understand the term state now, the state of a system, equilibrium, as well as stable and unstable states. I mentioned couplings. Couplings, again, are the relationships between the two parts, let's say ice coverage and atmospheric CO2 concentrations, right? Those are two parts of the system that are coupled, so they can affect each other. Coupled parts of a system have an effect on each other, and those effects can have feedback, right? Positive or negative feedback. And then there's the concept of linear or nonlinear behavior in systems. And this is very important for understanding when you might reach a boundary and how a forcing event might change a system from a stable state to an unstable state. And so let me quickly go into linear and nonlinear. Very few things are as linear as this space gun. Fire it. Now fire again using twice as much force. The shell goes twice as fast. That's linearity. Twice as much force, twice as fast. Let's take a camel in the desert and let's put a 250-pound weight on its back. It will bend. Now put another 250-pound weight on its back. It will bend twice as much. Now put a straw on it. That's nonlinearity. A small force having an effect out of all proportion. So linearity and nonlinearity will be very useful concepts for us throughout the year. You'll be analyzing systems and seeing whether they behave as linear or nonlinear systems. But for example, we could go back to our example of the climate system. And you can imagine that as you put in a certain amount of carbon dioxide in the atmosphere, it behaves linearly. So many units or parts per million of carbon dioxide, and you get a consistent amount of temperature change. And then you reach the threshold or planetary boundary in which you go over that point, and it has a much bigger effect. And that's because you're changing the relationship between all the various components of that system, ending or beginning positive or negative feedback loops, which can have a much more drastic effect than simply adding one more part per million of carbon dioxide. So you can go from what was a linear behavior to a nonlinear behavior, kind of like the camel example. So I'm going to go ahead and leave on the question about fractals, weather, and human population. It's a fascinating question. I hope it's one that you'll be able to answer soon. But I want to let you go on this podcast. So get on that reading, and we'll discuss next class.